All right, so welcome back to the second portion of the time series data mining class. Today we're going to talk about dynamic time warping or specifically about elastic measures. So as a recap, last time we started talking about how can we compute similarity or find the distances between two time series. We talked about the very first and most easiest way to find those, and these are known using LP norms. So LP norm is nothing but a family of method which relies on finding the pairwise distances between the time series. So this is an example of L1 norm where we're just taking the absolute value between the distances of every single pair of points between the two time series. We also talked about Euclidean distance, where we're taking the the square root of the squared distances square difference between every single point between the two time series. Now, one of the things that one that I should mention about this family of method is that they're pretty quick at computing the distances. It's because, as you can imagine, we're talking about the same index over here. So I is just a single loop that iterate throughout all the indices of the two time series that you're computing the distance of. So here, the main limitation as well is that the time series must be of equal length, right? So here I are the same index that we're talking about. So a single loop which iterates across all the indices of two time series which have the same length. They are quite inexpensive to compute, which means that the time complexity, because we're talking about a single loop, is only a linear time complexity, so big O of n being the length of the two time series over here. Okay, so in this class, we're going to talk about a second family of method known as elastic measures. So by the name, elastic simply means that they are not rigid. They're allowing us to pair some point coordinates, although they don't happen exactly at the same index. So on the left-hand side is an example of a pairwise measure, such as the Manhattan distance or an L2 norm, where here the limitation is that the two time series must be of equal length. While on the right-hand side is known as an elastic measure, such as dynamic time warping. It is elastic because, as you can see, the peak that happened on the first time series on the top, although did not happen at the exact same time spot, the timestamp of 21 ish in terms of x-axis, but it was able to catch up the peak on the second time series at around 25 time step in this case. So we say that uh, we are warping the time axis in order to make a better alignment in the two time series and catch up and catch up possible some possible peaks or pattern that happen later due to some natural or delays that might happen between sensors and regular everyday data capturing processes. So left hand side is just any distance Euclidean in Manhattan. Right hand side, as you could see, one thing which is very important to note here is that the warping or the alignment between every single point here do not cross lines. It's very important to keep that into mind when we talk about the pseudocode on how this distance measure is being computed. So those lines will never cross path, meaning that you will not see one point here crossing all over to another point, and therefore an overlap happening between those lines. So there are some rules that must be respected along the lines. Okay, so how can we compute this amazing elastic measure, a dynamic time warping, which is more intuitive, although as you might imagine, it might be a little bit more expensive to compute. The warping, a dynamic time warping is computed using something known as a warping matrix. So what is a warping matrix? A warping matrix is nothing but this 2D array where you're laying down on the x-axis the time series, one of the time series, and on the y-axis the second time series. Now the idea is that I'm computing values along all this warping matrix, and I'm finding what is known as a warping path. or also a warping function. So a warping path is a line along the diagonal, typically along the diagonal of the warping matrix, which shows us the best alignment between the point of the time series. As you might see here, this peak on the orange time series has been matched to 4 points on the left time series Q, which is the green time series, which means that, well, according to the dynamic time warping measure, this peak corresponds to 4 points, which are the corresponding peak point on the green time series, which is quite intuitive, as you could see. So, in fact, the slowdown or the valley or the downward pattern happens starting after the fourth point that has been matched from the peak on the orange time series. Okay, so there are multiple paths that you might choose along the warping matrix. Some of them might be very minimal, that minimize the total distance between the two time series. So in fact, if you take the dynamic time warping is nothing but the distance along the final distance, which happens on the right top corner of this warping matrix, which is nothing but the total distances that I captured so far on those red dots, plus the distance between every single point in that particular index that we have in here. There might be multiple paths which minimize the total distance, but we need to keep in mind that some of them are better than others depending on where they are located in the warping distance. In fact, staying along the diagonal and not deviating too far away towards the corner is a better warping path although it might be not the most optimal in terms of total distance in general. So we're going to see those rules as we move along the warping path in the next slides. Okay, so there are some rules as you move along the DCW distance warping matrix that we need to talk about. The first one is that there are only 3 possible movements from any point in the matrix, meaning that I can either go right or up or diagonal upward, which are the 3 movements that you could see in the slides, right? So either right, upward, or diagonal up. And the reason, or what's the rationale of this 3 movement limitation is that I want my path to be positively monotonic along the matrix. So meaning that I should always progress towards a positive path, towards a positive trend. I should not go back in time. If I go back, if I'm allowing myself to go left in the warping matrix, or downward, then what I'm allowing is those overlapping lines when I am finding the pairs of coordinates between the 2 time series, meaning that along these lines or alignments, some lines might overlap because I'm going too far in the back, right? So the fact that I'm allowing myself to go either right, upward, or diagonal up, I am making sure that there is no overlap between the lines along my warping alignments when finding the best alignment between the 2 time series. Okay, so that's the rule number 1. Now, how can we compute the total dynamic time warping between the 2 time series is the next question. Meaning that what is the DTW final distance between this orange and the green time series? Well, the formula is as follows, and there is a pseudocode in the next slide as well. So there are 2 edge cases that we need to first handle at the very beginning, and the first edge case is being that the 2 time series have a length of 0, meaning that I equals j equals 0. And in that case, of course, the distance between 2 non-existent time series is equal to 0, right? So that's pretty obvious, which is the very first edge case. The second edge case is when one of the time series length is equal to 0, while the other one is greater than 0. right? I equal to 0, j is greater than 0, or I or vice versa, right? So j equals to 0 and I greater than 0 in this case. Well, in that case, of course, the distance is equal to infinity, right? So the distance between a non-existent time series and a time series which has a length of at least 1 is equal to a positive infinity in this case. Now, the regular case, or the case which you're going to see in most of the times, is the third case scenario over here, which is nothing but if I want to find the distance between any pair along the matrix in this warping matrix. The distance between the dynamic time warping so far is nothing but the distance that I have accumulated so far, which is the first term, right? Distance between Qi and Sj plus the minimum between the three movements that will lead me to that point. I'll explain that in more details with an example, but the idea is that whatever movement will lead me to that point, which with the minimum cost in terms of distance, is the one that I need to choose for the next move along the warping path over here. So either I came from the right, or I came from the bottom, right? So I'm going upward, or I'm going with the diagonal. These are the three indices that were possible for me to come into that particular cell in the warping matrix. Okay, so this is a pseudocode which just translates the previous algorithm which I have in the slides over here. One thing to note here is that we're talking about a nested loop, right? So nested loop simply means that we're having a quadratic complexity. So you could see that the first loop indices moves from 1 to n, which is the length of the first time series, and the second one is from 1 to m, which is the length of the second time series. So the distance, the big O complexity is m times n, which is quadratic, quite expensive compared to just the linear complexity of the LP norms. And this is mostly due also to the fact that, well, here dynamic time warping is also allowing us to compute distances between time series of different lengths, which is a big advantage that we have here. So n does not necessarily mean that it has to be the same as the m over here. So one time series might be of length of 10, while another one can be a length of 15 or 20, for example. Okay, so now we're going to talk about the optimization of the DTW algorithms and some additional rules that must be respected while finding while moving along the warping path and finding this warping function over here. Some of them are mandatory, while some of them are optional here. So in fact, 3 of them are mandatory. The 3 first ones are absolutely mandatory and necessary conditions for computing the right warping function using this warping matrix. While the last one, the warping window, is an optional one. Some people like to use it, and we're going to see what that means in the next slide. So let's talk about the very first one. So the first condition is monotonicity. Monotonicity simply means that I want to stay on a positive trend pattern, right? So the path must be moving on a positive fashion from the left corner, from the bottommost left corner, all the way to the other boundary, the extreme boundary of the upward rightmost corner in my matrix. Continuity simply means that I should not miss any point of either time series along the path. So every single point, either from the orange or the green time series, must be aligned, or must be aligned with another point from the other time series counterpart. Boundary condition simply means that I need to finish all the points that I have from both time series, from I equal to 0 all the way to I is equal to m or n, right? So both boundaries must be matched. The last point of the green time series must be matched with the last point of the orange time series, and the first points are matched always by default. So this is the boundary condition of the dynamic time warping. Now, the warping window, which we're going to talk about later, will allow us to kind of restrict the way we move along the matrix. As I mentioned before, if I move too far out from the diagonal, then I am producing a lot of points which are, in this case, you could see 5 points have been matched from the orange time series to from the green time series to only one single point of the orange time series in this blue path, which I am highlighting over here. So these are not really good paths, although they might provide some low distance, right? In fact, that these are known as pathological paths. We don't want them because we are wasting a lot of points on only a small segment of the other time series. So therefore, if we restrict the path to be within some radius away from the exact diagonal from the warping matrix, known as a warping window introduction, then we are avoiding this problem of pathological path generation using your dynamic time warping distance. Okay, so here I'm just zooming in and illustrating some counter examples of each or a problem of each of these three mandatory rules of the DTW computation. The first one is monotonicity. As you could see over here, this is a wrong path. And the reason being is that it does not respect the three movements that were possible. In fact, here, as you could see, the path is going back downward on a downward fashion, and therefore it's not positively monotonic. This kinds of behavior will produce alignments which are overlapping, as you could see on the very bottom example over here. So if you see that at the end of the day, your points or your lines alignments are overlapping, this is probably a good sign that your warping path is suffering from a monotonicity property which has been violated. The second one is an example of a violation of continuity. And this is kind of obvious where one or of the points is missing alignments between the two time series. So here there is a gap in the path. So it's non-continuous path, which simply means that this point from the blue time series and this point from the black time series have not been matched. So in this case, the alignments are omitting some important features and some points have not been aligned properly. Okay, so here is a restriction of the boundary condition. And here it simply means that, well, the two time series have not been completely aligned together. So here the boundaries are, in fact, the very first point and the last point of the black time series have not been matched to any points to the blue time series over here. So this is a violation of the boundary condition. The warping window condition, the warping window is not a mandatory condition, but this is a violation of the warping window in case you choose to use a warping window as an additional constraint of your dynamic term warping. So warping window is simply saying that, hey, the path should not go outside of this radius, which has been predefined as a parameter of your DTW. And here the radius is nothing but everything which is inside of this a rectangle here, which is kind of like an envelope around the diagonal line or the perfect or diagonal line on the warping matrix over here. So here the path, or which is the blue or the black line over here, is outside of the radius, and therefore it is a clear violation of the warping window. And this is illustrated on the bottom figure over here, where we have way too many lines. About 80% of the black line or black time series have been matched to one single point from the blue time series, which is kind of a pathological path, not really a good path along to find using dynamic time warping. Okay, so this is an example of path or warping path problems along different DCW matrices over here. As you could see, I'm just going to give you a minute to think about what kind of problem each matrix is suffering from. And then we can discuss those in a minute. So you can just pause the video and then play it back once you find the problems. So the very first matrix is okay, as you could see. It does not have any boundary condition problems. It is perfectly continuous, monotonically positive. The second matrix, on the other hand, is suffering from a boundary condition. So the first point of the time series of the x in the x-axis has not been matched with the boundary of the first point of the y-axis time series. So the boundary condition is the problem of the second figure here. The third figure is suffering from the problem of monotonicity. As you could see, we're going backward, although it's positively going, but as you could see, there is a movement which is not allowed along the matrix, which is the diagonal left. Although I'm going upward fashion, but I'm going also on a diagonal left movement. Figure D, which is the last matrix over here, is obviously suffering from the problem of continuity. As you could see in the y-axis, 0.5 and index 6 do not have any alignment, right? Are not being aligned to any other point on the x-axis to the x time series. So although the first time series along the x-axis have been aligned properly, but the y1 or the second time series have not, 2 points or 2 indices have not been aligned in this case. So the problem here is continuity. Okay, so restriction along the warping function. We already talked about having a warping window. In fact, there are multiple ways you could do so. In fact, we're going to talk about two. The first one is the Sakwa-Shiba band. And here it's just a rectangle, a radius away from the exact diagonal over here. And the second one is taking into assumption that, well, it is better to be a little bit more restrictive at the very beginning of the signal, and then being a little bit more flexible when we're along the middle of the two signals, and then again restrictive again when we're closing and approaching the boundaries, the end boundaries or the ends of the two time series here. So the second warping function is, or the second restriction is a warping window, is known as the parallelogram or the Itakura parallelogram in this case. So another thing which I should mention is that if you pick exactly the diagonal, right? So what if a pad goes exactly on the diagonal between the two time series S and Q? So if we take exactly the diagonal, then we are producing an LP norm, or if you choose the L1 norm, then this is exactly equivalent to just computing a Manhattan distance, because you are just taking every single pair is being matched to the pair with the exact same index on the counterpart, right? So we don't want exactly diagonal. We want some kind of flexibility, something which moves monotonically positive in a positive trend, but also not far away from the diagonal as well. Okay, so now in general, right? In general, it has been found that the band, the rectangle band, is better than the parallelogram, which is also better than a simple, completely unconstrained DTW. And here, the violet color simply means that these are the possible places that can be used along the dynamic time warping matrix for finding the match between the X and Y time series. So in fact, empirically, and when I say empirically, is using in computer science simply means that using extensive experimentation, using a lot of benchmark data sets, it has been found that in general, when you're restricting dynamic time warping within some radius R, then using a parallel, using a rectangle approach, it is better than having an unconstrained DCW, and which is also probably better than the parallelogram. Here, the parallelogram has a strong assumption, is that, well, the flexibility must happen only at the middle of the signal, which is probably not necessarily correct for all the data set that you might that you might encounter. Okay, so this is an example of DCW algorithm at work. And as I mentioned, the very first step is to produce our really nice warping matrix. And here I'm just simply having the magnitude values of the X time series and or the red time series, and the magnitude values of the blue time series along the Y axis over here. So A and B are my red and blue, or vice versa, time series here. Now, how can I populate this DCW warping matrix? So as I mentioned, the population where we just need to follow the pseudocode that we had in the previous slides. So in this case scenario, we are not in any edge case, meaning that our two time series lengths are greater than 0, right? So we are typically on the third case scenario, where in order to find the value in every single cell in this warping matrix, we simply need to find what is the minimum value which could have led us to this particular cell, plus the distance, which here in this example we have been using the L1 norm, which is nothing but the absolute value between the two magnitude values of the time series A and B at that particular index. Okay, so let's try to do that with an example here on the slide. So let's try to find what's the number which is being produced over here. Okay, so the very first thing I need to find is what is the absolute value of a sub I minus b sub j, meaning that what is the L1 norm of 0 and 9. And here the L1 norm is simply 9, which is the absolute value of 9 minus 0, plus the second term over here is the minimum between three different cells, right? So what is the minimum between this cell or the cell which is on the bottom? And why am I highlighting those cells in particular? Because these are the only way I could have landed in this particular cell. I could either have come from the left or from the bottom here, exact bottom, or from the bottom on the diagonal level, right? Which reflects the three different movements which are allowed in the DTW. So either right or upward, or diagonal right in this case. So in this case, the minimum value is equal to 5, right? So 9 plus 5 is equal to 14, right? So 14 is in theory the number that should be in this particular cell over here. Okay, so that's how we compute the numbers along the warping matrix in this case. So let's try to do another one, but in this case along the edges of the matrix, right? So let's try to find what is the value over here. Try to compute 31 once more. So there is only one way I could have gone to this particular cell, right? Which is going upward, because I could not have used the right fashion because I am going out of index. I could not have come outside on the diagonal, right? Because that's again an out of index movement. So the only way I could have landed there is using the right or the upward arrow in this case. So the distance in this particular cell is equal to 25, which is the only way I could have been there, which is my previous distance, plus 7 minus 1, the absolute value of 7 minus 1, which is 6 over here. So 25 plus 6 is equal to 31, and that's the exact number which is being found in this particular cell over here. So if you do that along for all the distances that you have, all the cells that you have in this particular matrix over here, you're going to end up with your final DTW populated matrix over here. Okay, so this is the example that we just did over here. So the value is equal to 14 using the pseudocode and third case scenario over here. Now, how can we find the best warping pad now that I computed all those Windows values over here? So my warping pad is nothing but going backward in line in order to find this. So 15, and then I'm going to the minimum value that led me to number 15, which is 15 again, and then 15 here I either have come from 18, 15, or 14. So 14 is the value that I used, and if you keep backtracking over here, that will highlight the actual warping path of your DTW. All right, so now in theory, you should be able to understand how to compute DTW, why use DTW. It's a more accurate, although more expensive measure over here, and what are the constraints of DTW along or while computing the warping path along the warping matrix. Now, DTW versus Euclidean distance, what are the kind of advantages and disadvantages? We already talked about those. So the advantage of using DTW is that it produces more reliable alignments, and that's thanks to the flexibility for allowing us to kind of find alignment, although they happen later in time in one of the time series. The main disadvantage of DTW is that it's highly computationally complex, right? So it's quadratic time complexity in terms of big O notation here. The advantage of Euclidean distance or any LP norm is that it is cheap, it's linear time complexity, but it's not as accurate. That's the disadvantage here. Okay, so how can we use those using any k-nearest neighbor classifier? In fact, you can use those distances using your vector data set as well. So here, as an example, the age, income, and number of credit cards are just some numeric vector representation of each customer along this feature matrix over here. So here you could easily find what is the one nearest neighbor for each customer over here in order to classify whether John will have a class of yes or no for having a credit card or having a loan approval or not in the bank. So here, if you just compute 37, 50, and 2, the distance between the two vectors of John and every other vector that we have in the matrix, then we can find the nearest neighbor of John, which happens to be, in this case, Rachel, right? So Rachel has the lowest distance to John, and therefore probably the class of John is a yes. The loan of John might be approved based on the one nearest neighbor computation on the L2 norm. Okay, so these are just some results, error rates. So empirically, again, DCW has less error rates, but way higher. In fact, a few 3 orders of magnitude higher in terms of time, in terms of milliseconds over here. So it takes way longer to compute compared to just an LP norm or Euclidean distance. All right. Okay, so I'll stop over here. If you have any questions, please let me know. And please have a look at the handout, practice handout. Thank you.